then we'll start. Hey, did you know that people who take the bus or train are healthier? What? They get like 45% less likely to get sick, flus and colds. And somebody who drives. Did you know that? And they're around more, right? They're bigger, and they're also significantly healthier because they walk more. I don't actually drink coffee. I don't drink tea. Okay, ready to go? Mental break over. Oh, I've been recording this whole time. Ha, funny. Sorry, guys. Okay, let's think about this. Background. Okay, now you can use your brains. Oh, mental break over. Now let's think. Is it possible for root x minus 2 plus 3 to equal to 0? Be true for any value of x. Maybe. Okay, well, let's think about this. Root x minus 2 has to always be what? More than 2. Right? So you're saying that the answer has to always, with a square root, it's always going to come out as what? Positive or negative? It's always going to, right? Doesn't exist if you can't take the square root of negative. So whenever you get square root of some number, as long as it's within our domain, it's always going to be positive. So is it possible for a always positive number plus 3 to equal 0? Always positive plus 3 cannot equal 0 because we'd need a negative 3, right, plus 3 to equal to 0. So it's never possible. Since root x minus 2 will always be greater than 0. And if you take a positive number and add 3 to it, there's no way you can get 0. Have you ever heard the term extraneous root? No? Okay. Extraneous roots are very important. They are, so let's write out the definition, then we'll talk. A solution that emerges from the process of solving, but is not a valid solution to the original. So it's a solution that comes out that seems correct, but isn't. What's wrong? Did I do something wrong here? Okay. All right. So a solution that emerges from the process of solving, but is not a valid solution to the original problem. So algebraically, you start working, you start doing some things, all of a sudden you get an answer, but when you check it, it's actually not true. That is an extraneous root or an extraneous solution. It usually occurs when we square both sides. Because if you square a number, there could have been, right, the positive squared could have given that number, the negative squared could have given that number. So that's why if we solve algebraically, we must always solve and check. Always, always check algebraically, because we may have an extraneous solution. So if you square both sides during the solving, you have to always check. So let's solve this. So how do we solve? We're going to write the steps down below. So the first step is to isolate the radical. Isolate the radical. Okay, how do I isolate the radical in this one? Add 5 to the other side. We get roots x plus 2 equals 5. What do you think our next step will be? Square both sides. We need to get rid of the radical. So now that the radical is isolated, we can square both sides and eliminate the radical. Square both sides. We're going to take root x plus 2 equals 5. We're going to square both sides. Which gives me what? X plus 2 equals 25, and then subtract 2. So now we solve. The next step would be solve for the variable. X equals 23. And the very last step, what do you think that's going to be? Check. Check to ensure all solutions are valid. So no extraneous roots. A nice thing is, one way around it so that you have to solve algebraically on a test is I'll tell you to solve and I'll ask, what is the extraneous root? Then the extraneous roots only happen when you solve algebraically. And so you have to solve, you can't just use graphical, you have to solve algebraically to give me the extraneous root. Which one does not check out? So sometimes there's two solutions. Here there's only one, let's check it. And you always check with the original form. So does square root of 23 plus 2 minus 5 equals 0? 0 equals 0, yes. Left side equals right side. Okay, so next one I'd like you to try on your own. Maybe we should do it together. Let's just do it alone. Okay, let's try it. So if I did solve it algebraically, okay, so if I go ahead, minus 5, and you might have noticed already something's wrong here. Okay, and then we square both sides, boom, boom, and I get x plus 2 equals 25, x equals 23. So you check your answer, and what happens? You get 10 equals 0. But does 10 equal 0? No. So what would 23 be called in this case? Extraneous root. So no, this is not, x is not equal, it's extraneous. And therefore, there is no solution. Why is there no solution? Did you notice it in the beginning? This will always be positive plus 5. Is that possible? No. You might have noticed that right off the bat. Okay, turn the page. We're going to skip 6. But let's go through 1. Oh, I love my numbering here. It's awesome. 1. This should be, oh my gosh, 2. This should be 3. Oh my. Oh. Well, because there's 1 on the other page. Example 1. Oh yeah, 1, 2. This is right. This should be 3. No, we're good. This should just be 3. Silly me. Find the roots. Okay, this is a lot more fun now, a little bit more interesting. So isolate the radical. What are you going to do? Add x. Root 3x plus 3 equals x plus 1. What's our next step? Square both sides. What do we have to be careful here? Expansion of x plus 1. Guess what we're going to have to use? Okay, it's a perfect square, so you might be able to do this without actually writing it all out. But okay, what's root 3x plus 3 squared? 3x plus 3, the square root and the square cancel each other out, equals x plus 1 times x plus 1. So this is really x plus 1 times x plus 1, right? So when we FOIL that out, what does it give us? X squared plus 2x plus 1. Good. Remember with a perfect square, we multiply these two together and double it for the middle term, and then square the last term. Good. Okay, how do we solve a quadratic equation? This goes back to quadratics. Get it all on one side. Good. Get it all on one side. One side has to equal to 0. So subtract 3x, subtract 3. We want to move them over. 0 equals x squared minus 5, nope, minus x cubed, and take away 2. Okay, now what? How do we solve quadratics now that everything's on one side? Did you get that? Factor. Factor! Factors! Man, it's like we just never studied quadratics at all. Okay, you guys like blocked it from your memory. 1, 1, 2, 1. Okay, which one's negative? Negative 2, positive 1. That would do it. So we have x minus 2, x plus 1. So what are our solutions? Positive 2 and minus 1. So you thought you got like run away from quadratics. Nope. So we have 2 answers. Can we blindly accept those answers? No, don't trust them. You must check. Question? Devinder, do you have a question? No? Okay. So check. Where do we check? We have to go back to our original. So plug it into the original. So start with, let's check with x equals 2. 3 times 2 plus 3 minus 2 has to equal 1. Root 9 is 3 minus 2. Does that equal 1? Yes. To show your checks algebraically. And now show x equals negative 1. Root 3 times negative 1 plus 3 minus the negative 1 has to equal 1. Okay, what is 3 times negative 1? Negative 3 plus 3 is 0. And minus a negative 1, what does that come out to? Plus 1. Does that work? 0 plus 1, does that equal 1? Yep. So there's 2 solutions here. 2 solutions, 2 and negative 1. They both check out. So are there any extraneous? No. We're good. So that's why you have to check. Just because there's 2 solutions doesn't mean one is extraneous. Yeah. You can square root 0. It's still 0. Yeah. You just can't square root a negative. Yeah. That's why the domain is greater than or equal to 0. Restrictions. Can we talk about restrictions a little bit, guys? Okay, so for this one, we know our solution, like there is a restriction on the square root, right? So we know our solution has to be that 3x plus 3 has to be greater or equal to 0. It doesn't tell us our solution, but we do know there's some restrictions on x. So subtract 3, divide by 3, x has to be greater than or equal to 1. It doesn't tell us our answer, but there's our restrictions. And does that work out? Well, these are both within that as well. Okay, but you don't have to show your restrictions for these because we're checking our work. We're just going to plug it in and check it, so you don't need to show restrictions. We're not graphing it. We're just solving. For graphing, the restrictions have to do with domain. Okay, where do you want to go with 4? Where do we start? Square both sides. So be very careful, because we have 2x minus 1 equals x minus 2. Can you want to try this one by yourself? Okay, try this one. Square both sides. I'm there if you need me. Okay. Okay, you should get x equals 1 and 5 and then do your checks. So always work with the original function. Always the original. Okay, that gives me, ooh, guess what happens with 1? Yeah, 1 does not equal negative 1. So 1 is extraneous. Is 5 extraneous? 5 is nice. 2 times 5 minus 1 has to equal 5 minus 2. 3 equals 3. Yay! So our solution is x equals 5. Ooh, this one's so scary. Hey, what if we have 2 square roots? Okay, if I squared right now, if I squared this side and I squared the other side, would that eliminate the square root? No, because it would be a perfect square. There would be a middle term you'd have to FOIL. Ooh, so here's my tip. Let's isolate the more complicated square root in this case. So we're going to isolate root x plus 16, and we're going to move the root x to the other side. We're still going to have to FOIL. We're still going to have a square root, but we're just going to have to square both sides twice in this type of problem. So let's make it as simple as possible by isolating the more complicated square root. Okay, so if there's 2 square roots, we're going to actually end up squaring twice. So root 6, x plus 16 equals 8 minus root x. Now, let's square both sides. Will I have to FOIL on the right side of the equation? Yes. In that left side, the square root and the square cancel each other out because you're squaring the square root. X plus 16 equals, all right, 8 minus root x, let's write this one out, times 8 minus root x. Let's FOIL that out. X plus 16 equals 8 times 8, 64. And then I'm going to get at 8 times negative root x, negative 8 root x, and another negative 8 root x. So minus 16 root x's when we collect the middle term. So I'm jumping there a little bit. Negative root x times a negative root x plus x. Remember, root x times root x equals x. Not yet. Before we square both sides, what do we usually do? Isolate the radical. Yeah, we're going to isolate the radical again. So minus x. Oh, what happens here? They cancel out. That's helpful. Okay, subtract the 64. Isolating the radical. 16 minus 64. Negative 48 equals negative 16 root x. Next step. I'm trying to isolate the radical. Divide by negative root 16. I could have squared both sides there, but it's a lot simpler if we isolate the radical first. Negative 48 divided by negative 16. Positive or negative 3? Positive 3 equals root x. Now, what do we do? Square both sides. Which is what? 9 equals x. Positive 9. Can be a negative because you can't square root a negative. Okay, so what do we have to do before we circle our answer? Check. Root 9 has plus root 9 plus 16 has to equal 8. What's root 9? 3. What's 9 plus 16? 25. Square root of 25 is 5. Does that add to 8? Bingo. There's our solution. All right, we're skipping 6. I'd like you to look at 7. The picture is not drawn very well. My apologies. It got shifted in formatting. Oops. But you get the idea. Josh is shipping several small musical instruments in a cube-shaped box, including a drumstick, which just fits diagonally in the box. We're assuming he's putting other things in the box as well, so it's not just such a waste of space. Determine the formula for the length d in centimeters of the drumstick. The length d of the drumstick. In terms of area A in square centimeters of one face of the box. What? Okay, so what do we want to call, it's the cube, what do we want to call our side lengths? S? You want to use S? Sure. S, S, S. S. Okay. So what do we know about A and S? The area of one face of the box. One face. Is it 2? S squared, S times S. S squared, S times S. Length times width. Okay, we know that. How can we relate D and S? Is there a way we can relate D and S? No. Okay, you're getting there somewhere. You're kind of going down the Pythagorean route, right? We know this is S, right? The height, if we see that right triangle in there with the diagonal, that's S. Could we solve for this red diagonal at the bottom? Yes, because we know, is this going to be a right triangle on the bottom? Yeah. So we know, what do you want to call that? I don't know. C for now? So C squared equals what? S squared plus S squared. What's S squared plus S squared? 2S squared. Do you know what I saw in your quiz yesterday? A bunch of you added the exponents, right? When we add like terms, we keep the variables and the exponents the same. Just add the coefficients. What's the next step here? Solve for C. Square root both sides. Can we simplify square root 2s squared? What can we pull out? The s squared. What's a square root of s squared? S. So this could be written instead as root 2s. Square root of s squared is just s. So now we have the other triangle, which is s is the height. We have our drumstick diagonal, and then the base of the bottom diagonal is root 2s. Can we now make it relate s and d together? With what formula again? How would I set it up? B squared equals s squared plus bracket root 2s squared. You with me? So not really. Because we have the right triangle on the bottom, and now we have the vertical right triangle, the one standing up. We're using Pythagorean. So we're now dealing with this right triangle. Well, that's a thick highlighter. Okay, so now we're relating that right triangle. We were before using this right triangle on the base of, it doesn't look like a right triangle because it's a three-dimensional shape, but it is. Okay, well, d squared equals s squared plus, what is, when you square root 2, what is that? Root 2s, what does it become? 2s what? Squared. S squared plus 2s squared. How many s squareds do we have? 3s squared. Now what? Square root both sides. And we get d equals, can we simplify that? What can we square root? We can square root s squared. What's the square root of s squared? Just s. So root 3s. Okay, so originally we had area equals sides squared. But we want to relate everything in terms of d, a and d. So how do we get s by itself in this previous question? Previous formula we made. Divide by root 3. And so d over root 3 equals s. And I'm not going to worry about rationalizing because I know I'm going to be squaring this. Because our area equals our side, which is our diagonal divided by root 3, all squared. I'm kind of rushing here. Sorry. What does that equal? D squared over 3. So there's our formula relating area and the diagonal. Now it said, what is the area of one face of a cube? And we're talking, this is just one cube face, not the full area. That holds a drumstick length of 23.3. So could we solve that now? 23.3 squared divided by 3. Tell me what that equals. To the nearest whole number. So the face of one cube. (181 centimeters squared). Okay. So you guys have a lot of work to do. Okay. So and I still want to go over your quiz if that's okay. Yeah, you're not upset about it? Yeah, some of you are. Okay, well, let's first talk about your homework. Oh, it's not on this one. I have it on, maybe it's this one. Beef jerky. Okay, so your assignment. If you look on the front sheet, so yesterday's stuff, solving graphically, you have this handout, right? So today's stuff is right here, solving algebraically. That's really important, okay? I would say do this first. Solve the algebraically stuff first. Then you can work on this and the handout. Second. So second, third. That's what I would say your order of priority should be. Okay. Now we have tomorrow's class to review, and you can work through some of this tomorrow and also do some review tomorrow. Your exam is Thursday. This is a tight, really like lots of stuff in a short amount of time this unit, unfortunately. Okay. All right, I'm gonna hand back your quizzes, and we need to go through a bunch of stuff, specifically your written. And the restrictions. Mohammed M. Sorry. Tanda, Tanya, Jason, Keith, Armar, Jordan, Shan, Adnan. Harwinder, Sonia,